In this video, we're going to be going over what a redox reaction is, how to determine oxidation numbers for elements, and how to balance a redox reaction using what's called the half reaction method. I'm going to apologize right now, this will probably be a bit on the longer side. In the next video, we're going to go over more redox balancing, but we're going to focus on acidic and basic solutions instead. You are going to need your notebook and you're going to need something to write with, and once you have those ready, let's go. Okay, so to start off with, oxidation and reduction. These terms involve transfer of electrons between substances, right? So first thing we want to go over is what an oxidation state is. So oxidation state is just showing the number of electrons something has gained, in which case its oxidation state will be negative, or how many it's lost, in which case its oxidation state will be positive. Right, so positive numbers indicate a loss of electrons, negative numbers indicate a gain of electrons. Oxidation is when an atom's oxidation number increases. What that means is that it's losing an electron. Right, so oxidation is losing electrons. Reduction is gaining electrons. Right, the reduction comes in the fact that its oxidation number decreases, it reduces because it becomes more negative. So for example, iron plus 2 becoming iron plus 3, it had to lose an electron to do that, and its oxidation number increased, so that's an oxidation reaction. Now there's a couple of nice mnemonics that you can use. The one I primarily use is oil rig, right? Oil rig, oxidation is loss, reduction is gain. Right, so oxidation is loss of electrons, reduction is gain of electrons. The other one that you can use is you can also talk about Leo the lion. Leo the lion says grr, right? So Leo says grr, so this is loss of electron is oxidation, gain of electron is reduction. Right, so either of these two mnemonics can help you figure out which way it is. Just use whichever one you'd like to use. All right, so we'll start off by actually calculating oxidation states for elements inside of a substance. This is based off of a series of rules. A lot of it comes from your periodic table and the charges of ions that we worked with previously. So first rule, any pure element in its standard state is 0. Right, so O2, N2, F2, all 0. Copper by itself is 0. Carbon by itself is 0. So any element, nothing. Any monatomic ion, so any single atom ion like sodium ions, lithium ions, magnesium ions, its oxidation state is equal to its charge. Right, so Na is +1, oxidation state +1. Magnesium is +2. Nitrogen, when it's by itself, would be -3 sometimes. Now some atoms, again, are defined. Group 1, everything's +1. Group 2, everything's +2. Aluminum's +3 because it forms a +3 ion. Fluoride is always -1. Oxygen is -2 like 99% of the time. The only time it's not -2 is when it's a peroxide. Those can be a little bit tricky and usually you don't see those. Hydrogen is +1 except when you have a hydride. So if it says hydride, the H is -1. Now, anything else you have to figure out based off of the rules, right? So let's say, for example, I wanted to do potassium permanganate, so KMnO4. Potassium is in group 1, so its oxidation state is +1. Oxygen, it's not a peroxide, so this is -2. Manganese, I have to figure out, right? So there are 4 oxygens, so 4 -2s is -8. +1 is -7. To cancel out the -7, because there's no charge over here, this manganese needs to be +7. right? So that's as easy as it is to figure out oxidation numbers, right? Just follow the rules and then figure out whatever's left over. Okay, so we're going to talk a little bit about the activity series of metals. Now, first off, we're going to start off with some good news. Good news is in AP chemistry, if you're given a reaction, that reaction will happen. So you don't ever have to be in a position where you go, no, this reaction doesn't happen. Either we don't form a precipitate or this substance isn't higher on the activity series. You don't have to worry about it. If it's given to you, it occurs. But with that said, it's still kind of nice to know how the activity series works because it can help explain a lot of phenomena. Right, so the activity series just ranks how easily a metal can be oxidized into its positive charged ion. Right, so the higher up it is, the easier it is for that element to lose electrons. When you are reacting a pure element with another substance, like in a single replacement reaction, that pure metal will only react if it's higher on the activity series than the thing that's taking its electrons. Okay, so for example, magnesium metal can be oxidized by hydrochloric acid because magnesium is higher than hydrogen. Iron can be oxidized by hydrochloric acid because iron is higher than hydrogen. But copper and gold do not react with hydrochloric acid. They cannot be oxidized because they are lower on the activity series than hydrogen is. That's why, for example, when you see hydrochloric acid being transported across the country in tanker cars, those tanker cars are usually lined with copper because it will not react with copper. All right, so now we'll get into some balancing. So this is what's called the half reaction method. You'll see why in a moment. So first thing that you want to do is assign oxidation numbers to every element, figure out what's being oxidized and what's being reduced. Then split each of those up into their own equations. So the element that's being oxidized will be one equation called a half reaction. The element that's being reduced will be a second equation. That's our second half reaction. And you write both the reactant and what it would form on the other side. Once you've written your two half reactions, first thing you do, like any other equation, is you balance them for mass by using coefficients. After they're balanced for mass, you have to balance them for charge now. To balance for charge, you can add electrons to either side of the reaction to balance the charge. Charge doesn't have to be zero, they just have to be the same on both sides. After they're balanced for charge, before we combine them back, we have to make sure that the number of electrons in each reaction is the same, right? Because if something is donating 6 electrons, there better be another reaction taking exactly 6 electrons, right? So the way that we do that is least common multiple between the two reactions. Just multiply them up so the electrons are the same. And then add the reactions together, and whatever cancels, cancels. Right? And once you've gotten that done, you're done. That's half reaction method. All right, so take a moment, pause to finish writing down these rules, and then we'll pick up with an example of this. Now, the example, I will preface, can be done without doing the half reaction method, but this is just kind of a proof of concept of how it works. All right, so here's our example. We're going to take aluminum foil and we're going to put it into copper chloride solution. So first thing I'm going to do is I'm going to write out the equation for this reaction, right? So aluminum metal plus copper chloride solution, single replacement reaction, aluminum and copper switch places, we form aluminum chloride and copper metal. So now what we're going to do is, first step from this equation, we're going to assign oxidation numbers. First rule, all pure elements are 0. So aluminum by itself is 0. Copper by itself is 0. Next rule, monatomic ions are always their charge. So chloride right here is -1. Chloride is -1. Aluminum +3. Now again, if you notice, 3 negative 1s and +3 makes 0, which equals here. So that means for this copper, I have 2 negative 1s. This copper has to be +2. right? So now let's see what's changing. Aluminum's going from 0 to +3. So 0 on the reactant side, +3 on the product side. This is an oxidation, right? So I'm going to write my half reactions. My oxidation, aluminum 0 goes to aluminum +3. My chloride's not changing. It's -1 on both sides. My copper's going from +2 to 0, so its oxidation number is going down. That's a reduction. So copper 2 to copper 0 is my reduction. So these are my two half reactions. Now I'm going to balance them for mass. 1 aluminum on this side, 1 aluminum on this side, good. 1 copper, perfect. Now I have to balance for charge. The left-hand side is 0, the right-hand side is +3. Well, I can only balance by using electrons, so electrons are negative. So I'm going to put 3 electrons on this side of the equation. Right? Remember, it's an oxidation. Oxidation is loss of electrons, so electrons should be a product. And I'm going to make 3 of them. Reduction, +2 on this side, 0 as a product, means I have to add 2 electrons to this side. Right? So now this side is 0 and 0, and it's balanced. Remember, it doesn't have to be 0, but for this example, it winds up being that. Next step, now that everything is balanced for mass and charge, balance the electrons. I have 3 going out, 2 coming in. So that means I have to scale them up. Right? The least common multiple of 3 and 2 is 6. So I'm going to double the oxidation reaction. So 2, 2, and 6. I'm going to triple my reduction reaction. 3, 3, and 3. Now what I'm going to do, electrons, 6 here. Sorry, that should actually be a 6. 6 here, they cancel out. And now my final equation is just going to be rewriting the reaction, right? So I have 2Al. Now my copper 2+ is attached to chloride. So I'm going to do 3CuCl2. That will yield 2 aluminum attached to the chloride, so 2AlCl3 plus 3 coppers. And again, 2 Als, 2 Als, 3 Cus, 3 Cus, 6 chlorines, 6 chlorines. I'm balanced. Reaction's done, right? So we could have done this without the half reaction, but this is a good check to show, yeah, this is how it actually should work. So this is balancing a redox reaction. In the next video, we're going to work on acidic and basic solutions.